Okay, so we're going to go on and talk about chapter 19, and this is not on the next test, or it's not on this test, but it's on the following test. And although if you take speech classes, they kind of tell you never apologize and never say you dislike something. Like honestly, the this is thermodynamics. It's not one of my favorite topics. So I don't like stoichiometry as much. Like if you think about chemistry, like what chemistry is, like the chemical accounting, like I personally find it kind of boring. Like I think the really cool things with chemistry are I like the kinetics, like how chemical reactions happen, and ergo how you can manipulate chemical reactions to get them to do what you want to do. And I like the quantum mechanics stuff and like where the electrons flow and how things bond. I think that's really cool. But I also like how interconnected everything is. That's one thing I do enjoy about thermo is how connected it is to other topics. But as a whole, though, thermo is not as exciting, although my students tend to love it because it's very, very straightforward. And what I do like about it, like I said before, it's just it's amazing how thermo connects to everything, though, and it makes like I can't imagine how difficult life would be if this was not true. So we can talk about that a little bit later. So this is going to be like the next two lectures are going to be relatively straightforward, but it's also going to be not as much pizzazz, as the other ones. So hope you don't mind that. But I've also been trying to allude to a lot of things in these next couple lectures. Like I talked about entropy before. Entropy is disorder, and so I mean, I mentioned it before, but before this class, but we'll talk quite a bit about entropy for the next two lectures. So sometimes it's also referred to as the heat tax, meaning you can't break even. So this is one of those impossible pictures. So you can see here in this top one, it says heat tax, and over here it says free energy. And then you have this perpetual motion machine where the water flows and it turns a turbine here. So it turns this turbine, but then the water flows this way and then keeps on going. The idea is you can have perpetual energy this way. And perpetual motion, though, at least on a macroscopic scale, like large things, it can't happen. I mean, you can have a single molecule can spin around forever. That's fine. That's okay. But having a wheel just continually spin and spin and spin, that's impossible. In order for this one to be true, this own machine, water would have to flow uphill randomly, and that is something that's not going to happen. So that's the flaw with this design. So, but one of the reasons we can't break even is because of entropy. So let's talk about electricity generation. So how we generate electricity. So, and this is the load profile for Oahu. So this one right here. Ooh, I shouldn't use the eraser. This is the load profile for Oahu. We are slightly similar in Maui. We've changed quite a bit over the past few years, mostly because of the solar telescope. So that actually the solar telescope is a huge draw of electricity at night. So we actually do reach our capacity for electricity in the evening. But how most of the electricity is generated is at least more than half, let me think. So coal is about 45% and about 20% nuclear. So definitely more than half. But the idea how we get most of electricity is we have some sort of heat, and I, drawn it with my PhD in chemistry, artistic skills, a flame, nuclear reactor, some source of heat, and we have water. You have water here, and the water boils, and then the steam goes up, and it turns a turbine. Okay, a turbine is just a fan, basically. So, and typically though, what we do is we have here, which is called superheated steam, if you remember, when we were talking about the heating curves. And so this all typically stays as steam. And this is also, I mean, similar to the 350 megawatt plant that we have on Maui. That's how we generate electricity is this way. It's kind of it's a really old technology. I mean, we use diesel fuel here, diesel number 2 specifically, and the boilers, for instance, this is the boiler there. That they're pretty old. So but boiler technology is just a tank that you boil water in, so it's not too surprising. But we also here we superheat steam, so the steam is high temperature here. As it turns the fan, it gets cooler, and then the steam goes down. We condense the steam with a heat exchanger. So when you see something like this, that means heat exchanger in schematic drawing. So heat exchanger, and then you get liquid water, and then that then goes back into the boiler and boils and so on. So the turbine turns a generator. So what is a generator? A generator is just a wire. So you have a metal wire, and you have magnets, and you spin magnets around the wire. So the alternator on your car works in the same way. So something that generates electricity. So and here in the United States, we have our generators at 60 hertz. So 60 times a second. In Europe, it's 50 hertz. So they have 50 hertz generators. So it just depends on where you're at. So it's 50 to 60 hertz is typical for the world. So hertz just means numbers per second. So here we have our 60 times a second turning. And another interesting fact, due to decreased load on the electricity systems here on Maui, they actually the frequency upped to like 62 or 63 hertz, and it messed with some of the clocks. I've noticed this a little bit, like the clock on my microwave. I'd have to change it, set it back a couple times because the time was going faster. Because of the fact that the frequency was slightly higher during the main part of the pandemic, the clocks after a couple months would be ahead by like 10 minutes or something like that. So I'd always have to change the clocks because there's some of those clocks work off of the frequency of the AC, the alternating current coming in. So other watches, though, I mean, I've got a cheap digital watch here. These usually work by usually you have a crystal or something like a piece of quartz, and you run electricity through it and it vibrates. And this one won't lose the time because it's not connected. It's connected by a battery, but I mean, it's just working off the vibrations of a crystal is typically how these things work. But some of the cheaper clocks that you get on like microwaves and ovens, they run off of the frequency of the electricity coming in, which is supposed to be 60. But anyways, so generator, and so like I said, it's just a wire. So you just have a wire, and you spin magnets around a wire. If you take, I guess I have the arrows, pointing in different directions, but either way. That induces what's called an EMF, an electromotive force, in the wire. So, or in the conductor, I should be more specific. The conductor, the magnets moving around, and if you study physics, it's the right-handed rule. So if the things are twirling this way, it means the current's going to go this way by your right hand. And also we have positive. I'll talk about this next chapter, but the way we do electricity is wrong. It's backwards. It's the negative charges that move, not the positive. But either way induces the magnets moving, induces the electromotive force, and then the force is then carried along the wire. So you have the electrified you have the electrified high tension wires, and then it comes to your house, and then you turn on your stove to boil your pot of soup or whatever. So what do I mean by heat tax? So if I have 1,000,000 joules of heat from a flame, is all that heat going to heat the water and boil the water? No, of course not. So it's you're losing heat that way. Not all of it is being transferred to the boiler to boil. Also, the boiler itself, it's not going to be perfectly insulated. It's going to be releasing heat that way. And does all the energy from the superheated steam turning the turbine, is all of that energy transferred to the generator? And the answer is no. No, of course not. Because it's a fan, and the fan is moving. There's friction. There's drag. So there's just from the just little bit of air, there's drag and the gears moving. There's the friction of the things moving. Just it gets warm. I mean, hopefully it's well oiled, but not all of the energy is transferred. Some of it is lost to heat. So friction turns into heat. Same thing with a generator. Generator has moving parts. You're going to have losses of friction. And as all the energy coming from the generator to the high tension power lines go to your house, is there energy losses there? And the answer is yes. Yes, there is. As the current is flowing, it loses energy. But one of the ways that you can limit the amount of energy that's lost is you can have high voltage. So talk a little bit more, but power is going to be the voltage times the currents. So no, it's the power in watts is the voltage times the amps. Amps is so the voltage is joules per coulomb, and amps are coulombs per second. So coulomb is a charge. So you can think of your amperage as, like, if you think of a river flowing, so you can think of the amperage as like the water, how much water you have. If you have more water, you have more currents. And you can think of the voltage like how much energy each of the water molecules has. And they're interchangeable electricity wise. You can change voltage and current interchangeably. I mean, well, you have to transform it. You have to use a transformer, but you can change the energy that way. What they do in the high tension lines is they up the voltage. You have really high voltage, relatively low current to the voltage, and that reduces the amount of friction. So because electrons are moving, electrons are negatively charged, and they're moving, and they rub up against each other. So as they rub up against each other, it creates friction. That's resistance. Another word for that is resistance. And resistance generates heat. So high tension wires, I've never really gotten close to one, but I imagine they're probably kind of hot. So I don't really typically see snow on them like areas. I mean, it doesn't snow here, at least not at this altitude or very frequently, but I mean, you in general don't see a bunch of snow around high tension wires. So I'm assuming it's kind of warm. So, and if you wonder what the level is, they're usually between 100,000 and 10,000 volts. So some of the big high tension wires, 100,000 volts, and then typically the current or the stuff going into your homes is around 10,000 volts. So, but of course it depends. I'm not sure. I have to ask my neighbor who works for the electric company. I don't know what they do here in Hawaii as far as the voltage. So, and so you have energy loss there. And then finally you turn on your stove and you have your heating elements. So your heating element is all the energy from the heating element going to your pot of soup. And the answer is no, right? Because if you put your hands up in front of the stove, you can feel the heat. So you're already losing quite a bit from radiation. By conduction, it's heating up the stove itself, right? So you're losing it that way, and also to the air, and then you're heating the pot as well as the soup. So you're having a lot of it's a lot of energy is wasted just by turning on your oven, right? So just think about it, right? You have from the flame here in Maui is diesel number 2. So we have a diesel number 2 heating the boiler. So we're having energy loss there. Turn the turbine, energy losses there. Generator, energy losses there. High tension wire, energy losses there. And just even heating up your oven, there's energy losses there. So we're losing quite a bit. And that's what we call the heat tax. So although you're paying for the kilowatt hours, and also electricity. I haven't seen the electric bill this month yet. I'm kind of scared, right, because of the price of oil going up. So we're losing quite a bit to efficiency. Or we have, but I mean, there's only so far we can go for as far as efficiency. So here's the load profile for Oahu, and what I have here in blue. So this is typically, so this one there, this is typically how the rest of the country goes. You have a bit of a baseline, and you want a baseline, and then for most of the country, usually between 8 and 5 is what's known as peak hours, and that's when most electricity is consumed. And then it drops off from 6 to 9-ish, and then at evening time, you typically have your base, and you have the base until people get up in the morning, right? So, we don't typically have our peak in Hawaii actually is around like 7, 8 p.m., 6, 7, 8 p.m. And the reason why is because we don't have industry here. So our number one industry in Hawaii is tourism. So it's tourism and just people services, right? So I mean, I'm in a services economy, right? I'm a teacher. I'm teaching you guys. You're receiving the service of academia. So we don't typically manufacture anything. We do some things, but very little here in Hawaii. We don't make many goods going out. And actually one of our major exports in Hawaii is jet fuel. So just because we have so many planes flying it. So, so because of that, but then when we go home, what do? We turn on our ovens to cook dinner. We turn on our television sets, watch our Netflix, blare our music, that kind of stuff, and that's why we see these heavy peaks later in the day. And so what about baseline? What is baseline electricity? And a lot of it is for civil defense as well. So I mean, there's things that we want to have on all the time: traffic lights, hospitals. It's nice to have a hospital all the time, right? Can you imagine, like, all right, well, I broke my leg and I'm in surgery, and like, well, no, I'm sorry, lights are out. We got to pick up this surgery tomorrow when the lights come on at 8 o'clock in the morning. So just hang tight. Like, no, of course not, right? I mean, we have the hospitals on 24/7. We have emergency services available all the time for that. Also, surprisingly, I thought it was surprising, food storage. Food storage is also on baseline energy. So here specifically fish. So refrigeration for fish. So that's one of the people that often ask for emergency power. So if there is ever a power outage, we also have emergency power available. So I mean, the hospital has their own generators, so the hospital's set, and typically some of the people that ask for power are anywhere that stores food. So Costco, Foodland, Safeway would ask for power because of their refrigerators and freezers, and also so fisheries, the people that store the fish, they're typically always want to have power available. So they're on the list where where they get prioritized for emergency power. So that's the baseline. What's interesting though about Maui is that our baseline is actually raised quite a bit. Well, I guess it's not necessarily the baseline, but typically, so for this type of setup, where you have kind of the old-fashioned way of doing things, using a hydrocarbon to generate steam to turn a turbine, they keep it at the same level all the time. So and because just turning things off, it just takes a long time for it to reach steady states. Except for gas turbines. Gas turbines can turn off and on at will. But the steam turbines you need to have on all the time. And what is happening now is the Daniel K. Inouye solar telescope. So that is actually eating a lot of electricity at night, which actually it's a good thing though, because we wouldn't have used that electricity anyways; it would have been wasted. So what they do at DKIST, so the solar telescope, they generate ice at night. So they have huge ice machines that generate lots of ice, and then they use that ice to cool the telescope during the day, because a solar telescope obviously is going to operate during the daytime, but it's among other things, it's infrared, and you have to cool the so when you're looking at the mirrors, the infrared mirrors and detectors, your mirrors and detectors have to be relatively cool, because otherwise it will pick up the infrared light just from the instrument itself. So the instrument there has got to be really, really cool. And the way that they cool it is by ice, like solid water ice. And they have the ice machines run at night so that they can consume that extra electricity. So that's actually I think that's an interesting idea. And that's great that they're using electricity at that time of day. I mean, it's better than using electricity at this time of day, because that would draw away during the peak hours. So one of the problems with this though is we, with these heat losses and electricity and loads, the need for baseline is alternative energy. And that's one of the problems with alternative energy is when we have it. And so if you look at solar, so here is the typical a solar output, and obviously solar power generates electricity when the sun is shining. So and a problem for here in Hawaii is, I mean, it's great for the mainland because the peak hours are during the day. Here in Hawaii though, the peak hours tend to be later in the evening. So what's happening to all the solar energy? And it's, in some ways, it's generated at the wrong time. I mean, they still take some of the load off, but then again, for like a plant like we have here on Maui, it's always on. It's always on. We can't ramp it up or shut it down. A gas turbine you can, but not a steam turbine. So, and that's a problem with solar power. And also, it's probably not as smooth as this curve. It's going to be, clouds are going to come over, cloud coverage. Of course, if it's a cloudy day, there's less solar power, and so on. So, but one of the more dangerous, well, not dangerous, another one is wind. So here, for instance, is a capacity. So estimated power generation with a capacity of 2 farms, the capacity of 2,800 megawatts. So this is a wind farm with a capacity of 2,800 megawatts. So this would be like 6 nuclear power plants. This is a lot of power. Nuclear power plants are usually between 500 and megawatts and a gigawatt. So, and these data are from Canada, and you can see that wind power just doesn't generate very consistent energy. And so here are data also from here. So again, this is Canada. This is Canadian data. So it's not going to be as shown for in the same way as Hawaii. So if you see here, you can see these lines up and down because people use more electricity during the day in the mainland. So at night, not so much. So you have the day-night shift. And you can also see here in in June, July, the power generation, the amount of energy you need goes way down. Where it's opposite here in Hawaii, because if you look at Hawaii, so summer is, I guess it's similar. I wonder why winter is more. I was gonna say because of the climate control, but I guess that's not necessarily true. So summer does go down. No, I guess people actually use heaters here. So similar to Hawaii, the energy goes down, energy consumption goes down in the summer. I would have thought it went up because that's when I turn on my air conditioner. But then if you have medium winds, this is when you have the power that comes out from an area of well, capacity 2,800 megawatts. And with the combined cycle, so you have the electricity dispatched with a combined cycle of gas-fired power plant and wind farms, single wind farm. So like I said about natural gas, like a gas turbine, you can turn them off and on. So they can handle a peak load a little better. So, but you can see though with medium wind, you're getting spots where you're getting no power generated. And that's when you have, if you have a big grid, so Canada's on a big grid, and you're going to draw electricity from other parts of the grid then to make up for the areas here of zero generation. And also counterproductive for wind energy, you don't want high wind. The best type of wind is low wind. So you want slow, steady, low wind. You don't want high wind, because you can see, just looking at medium wind versus high wind, you're just getting these areas where you're hitting zero. And if it wasn't for the connected grid, you'd be in trouble. So what about Hawaii? You can see that we do here on Oahu, this is bellows. So you can see the wind still jumps up and down, even in a very windy place. And also here on Maui, I mean, in the wind here, right? The wind picks up around noon or 1, right, with the trade winds coming in. So we do have high wind here, but it varies. At least, I mean, it's the wind does pick up a little later in the day, but in the morning we don't have that much wind. So you have to have something. Wind alone wouldn't solve our energy problems. So we need more. We need something. And then what do we do though with wind? So, I mean, how do you store the electricity? I mean, what do you need to do? I mean, like, one of the things that's great though, hydroelectric. Hydroelectric is an awesome alternative energy because it's very steady. Water's density doesn't change very much. So if you have a reservoir and you run the water, turn a turbine, so that generates very steady electricity. The input is very consistent, and the temperature doesn't vary very much. I mean, it's vary, probably on the order of at most 10 degrees Celsius, maybe even less, right? And density of water doesn't change that much anyways. So, and gravity is pretty consistent, here. So the falling water is going to have a very consistent output. So versus wind, what about wind? I mean, so if you've seen a hydroelectric plant, they're small. They're not very big at all. And what about windmills though? I mean, they're huge, right? I mean, you can see them on the hill there on on West Maui when you're going towards Lahaina. We have you can do the poly trail. My wife loves going on that trail. So I think it's kind of hot sometimes. But I mean, going up there, the windmills are huge. Like, why are they so big? Because air is about 1,000 times less dense than water, where hydroelectric plants are really tiny and air just not a lot of matter there. So you need to have big turbines to generate electricity from them, and to capture the effect of all that matter. And the matter is it's the vapor phase. It's not the condensed states. So there's just not a lot of matter. So maybe if it were on Venus or something like that, or I don't know, Neptune apparently is a very windy planet, but of course it's a gas giant. I don't know how if you'd float the turbines or something like that. Maybe that would be different because Venus has an atmosphere about 100 times as dense as the Earth. So maybe that would be different. I don't know. But here on Earth, though, now mind you, alternative energy is great and important, but it's hard to make it work compared to fossil fuels because the fossil fuels are just so consistent. And something like hydroelectric, which is a wonderful thing too. And of course, there's ecological problems with all of these. It's not a perfect solution either because hydroelectric, it damages the hydrosphere. So the aqua plants and animals have an issue with that. So it's something, and we're trying to figure it out. And one thing about Hawaii, we have our own grids. We don't even have a single grid going around Maui, right? Hana has its own grid, for instance. So we don't have everything interconnected. So and if you look at the United States, we have 3 grids. We have an East Coast, we have a West Coast, and we have Texas. Texas has their own grid. So also we share some of our grid with Canada as well. So the East Coast one goes up through to Niagara as well. So we have all that grid being shared with our neighbor up there. So but like I said, we don't have that here in Hawaii. We have, and we don't even have a continuous grid in every island. So it's an interesting solution or interesting problem, and that's one of the reasons why you see more wind farms and stuff going on here. They're doing research on wind to see how well it works. So we'll see. That's a problem. Thermodynamics is a problem with wind. So, and let's talk about thermo in general. There are some limits to thermodynamics. So you can tell what the end products are. So it's your magic crystal ball, kind of thing. Thermo will tell you what's going to happen. With absolute certainty, it'll tell you what'll happen, but it won't tell you how quickly it happens. So I guess I don't have too much bling on me today. Diamonds, I guess I can't show you a diamond, but diamonds, so diamonds are formed, they're a form of carbon. And under intense heat and pressure, the most stable form of carbon here at this temperature and pressure is graphite. And if you take graphite and you put it under heat and pressure for a long period of time, it'll slowly turn into a diamond. And the opposite is also true. If you bring a diamond to the surface of the earth at this temperature and pressure, it is thermodynamically unstable. And over time, without a doubt, absolute certainty, a diamond is going to turn into graphite with absolute 100% certainty. But how long is that going to take? Hundreds of millions of years-ish, right? So that's what I mean by thermo. Like, it'll tell you what'll happen, but it won't tell you how fast. And we have no way of knowing. That's a completely different field of study. That's kinetics. So that's how fast something to happen is not connected to this at all. So you cannot use thermo to predict how fast something will happen. So, and I think about this sometimes because a lot of jewelry, it'll contain different types of precious metals, gold, platinum, lined up next to each other, different alloys of gold together. And the truth of the matter is those different alloys are going to corrode the other ones. But how long is it going to take? Hundreds, if not thousands of years. So it's probably okay. So your gold platinum band wedding ring is going to last a couple lifetimes. So, right. So I guess they still have these commercials. I don't watch TV with commercials anymore. Like diamonds are forever. That's a De Beers marketing ploy. Diamonds aren't forever. They will turn back into graphite. But like I said, it'll take millions of years, hundreds of millions of years. So, since civilization is only 5 million years or 5,000 years old, so it might as well be forever if it's a couple hundred years. Okay, and then spontaneous, couple definitions. Spontaneous reactions can be spontaneous. So an example of a spontaneous reaction is iron rusting. If I were to take a block of iron, I set it on the side table I have over there, it will rust. You know, it will, in this environment, it's going to rust. So if I put next to the block of iron, if I had a pile of rust, is the rust going to turn into iron? The answer is no. That's a non-spontaneous reaction. Can you get non-spontaneous reactions to happen? Yes. Yes, you can, but you have to do things to them. So the way that we turn rust into iron is we reduce it with carbon. You take coke carbon and you heat it up really hot, and you can turn iron oxide into iron metal. So that's you can do that in a forge. You can do it in a big plant. You know, so that's a non-spontaneous process, but you can get it to happen. And this is just like people. I mean, think of it like people. Like if you ever have any really spontaneous friends, they call you up saying like, hey, it's Tuesday. Like, you want to go skydiving? I'm going skydiving. It's Tuesday. You know, time to go jump out of an airplane. I'm like, I'm relatively non-spontaneous, but like, no, you know, I got to go work. You know, can you get someone who's non-spontaneous like me to do something like jump out of an airplane? Well, probably not. I'm afraid of heights, first of all. But secondly, you know, like, all right, if you jump out of an airplane with me, I'll give you $1 million and a new car. You know, then I'd probably do it. Right. So, because then, you know, you're giving me an incentive. So how do you get rust, iron oxide? How do you turn iron oxide into iron? It doesn't want to. But how do you do that? Well, you give it lots of heat energy and you give it electrons from carbon. So you get electrons and you get heat. Enough electrons and carbon and heat will turn iron oxide into iron. So you can take a non-spontaneous reaction to happen, but you have to cajole it. You have to do something. And there's endothermic. So I mentioned about that you have the heat tax, the heat loss, and I mentioned before is entropy. Because of entropy disorder that's all happening. Why do we have endothermic reactions and processes happen? So ice melting. So ice melting is endothermic, right? So if you hold ice in your hand, it's cold. And as the ice is melting, it's cold. It keeps on being cold. So why is it cold? Because as ice is melting, it's absorbing the heat of fusion. So it's 6.01 kilojoules per mole of energy as the ice is melting. And that's endothermic. It's the positive direction. It's absorbing energy. Why is that happening? Why, I mean, so why does an endothermic thing that requires heat, you know, like why is it happening? So, and it's, part of it is in part because of entropy. And we'll also talk about free energy coming up. So how some of these other processes happen. So entropy. So entropy, and I keep on giving all these things. So the actual definition, there's two definitions of entropy. So entropy, one of the definitions is, so this is actually the official definition. Entropy, and we give it the letter S. So S entropy is equal to a constant, Boltzmann's constant, so times the natural log of the number of states. So, which means if the number of states is large, the entropy is large. And the other way to think of it is if you have few states, or even if you have one state, if you have one state or few states, there's very low entropy. And coming up, that's the third law of thermodynamics. The third law of thermodynamics says that a perfect crystal at absolute zero has no entropy. And because a perfect crystal has only one state and the natural log of 1 is 0. So the natural log of 1 is 0. So that's the good old third law of thermodynamics. It just reinforces the definition of entropy. Entropy can also be defined and calculated as the reversible heat transfer divided by the temperature. So that is very frequently used. But the most proper definition, though, is this one. That entropy is this, the Boltzmann constant times the natural log of the number of states. So, which means that the higher the entropy is proportional to the number of energy equivalent states. So energy equivalent states. So let's look at these. So here's some examples of low entropy. And now keep you in mind, we're dealing with 4 particles. Typically, we have big numbers. I'm going to throw a number out there, something like 6.02 times 10 to the 23rd particles, for instance. One of my favorite numbers. But we're going to make things simple and just look at 4 numbers. So imagine we put 4 gas particles into a chamber, and then we open up the chamber. And what's going to happen? So we start with some really low entropy, very high ordered. So low entropy means high order. High entropy means high disorder. So you can't have all the gas be in one bulb, and you can have all the gas be in the other bulb. So, but what if it's evenly distributed? So, and there's only one state of each of these. So if you have 4 gas particles, there's only having all of them in one bulb. There's only 2 states like that. Then, if you have, so if you open it up and then you have 2 gas particles in each of them, it's much more likely that, it's one out of, there's only 1 state or 2 states, to be say, for having in one of the bulbs. If you look at the number of states, and this is just this is just probability. So if you have gas particle 1 and 2 here and 3 here and 4 here, well, you can have 1 here, you can have 1 here, and then you can have 1 and 3 here and 1 and 4 here, for instance. But this is just by probability. It's much more probable that the gas becomes evenly distributed. So, and I don't think I have to talk too much about this. I think it's probably pretty obvious that this is, or do you want me to go through more of the math on that? Is this obvious to you guys that the gas, it's more likely, there's more probability of something happening that the particles are evenly distributed. Another way, if you can think about, like, does anyone ever play craps, like the dice game in Vegas? So how often do you roll, 2 or 12? And it's very infrequently. How often do you roll a 7? Like, much more frequently. Why? Because there's just more combinations that add to 7, whereas there's only one combination that adds up to 2 or adds up to 12. But 7, there is a much greater probability for that. Same thing for this. There's a higher probability to have 2 particles in each of the bulbs than to have all the gas in one. And this is just with 4 particles. So let's say instead of 4, we have a big number like 6 times 10 to the 23rd number of particles, right? So when you're dealing with things, processes like that deal with atoms and molecules, there is no way that it's not going to be evenly distributed. It's going to be either evenly distributed or very, very close to it. So, and this was a big deal for people in the 19th century. As we were studying this stuff, actually it was a belief, like a lot of physicists thought that all the questions of the world were going to be answered. And physics was almost like, even today it's less so. A lot of philosophy was in physics, and And people thought like, okay, well, if we can figure out where we are and where we're going, then this is great. We'll know everything. We'll know exactly what to invest in. We'll like, and a lot of people believe in fate. Like things have already been written how they're going to go. So once we can figure that out, then it's all good. But then quantum mechanics happened in the 20th century, such that you can never know the position and momentum of something. And even before that, they figured out like, oh, one of the major driving forces in the universe is probability. Like it's just simple mathematical probability. And then the more likely something is to happen, the more the more opportunities that something has to happen, the more likely it is to happen, the more often it's going to happen. Like if I'm playing dice, I'm going to roll a 7 a lot more than I'm going to roll a 2. And same thing with gas particles. If I'm studying heat transfer and fluid flow and where things are going, it's much more likely for the fluids to be evenly distributed by temperature and by concentration and so on, because it's more probable. Like, and if I even so, like, say I put a concentrated something in there, it's gonna flow towards non-concentrated because that's more probable. Like, oh, that's horrible. And like, I thought it was fate, but it turns out just math. So it hit people pretty hard. So like this day and age, it's not as painful, I think. But and also, so things go and processes flow. Time flows from high entropy to low entropy. So from more ordered, fewer states to more disorder, many states. And so I keep on using states and disorder interchangeably. So think of a clean room. What does a clean room look like? So if you go into someone's bedroom and if all the clothes are put away in your dresser, and if I open up the dresser and look at your socks, if your socks are all matched and folded and put together in a certain ordered fashion in your sock drawer, and if I open up and you have your t-shirts folded and maybe they're even sorted by color, that is a very ordered system. So that is low entropy. That's ordered, that's low entropy. What is a disordered room like? Socks are all over the place. They're not matched. T-shirts not in the dresser, all over the floor. Maybe one's hanging on a lampshade. So how many, that is disordered. How many states are there of a dirty room? There's many, many, many states. It's much more probable. So entropy-driven processes, so geared towards disorder. So that's kind of, I mean, that's, kind of a colloquial example, although it takes energy to keep things disordered, it's, as humans, at least for me, once I get things ordered, it's easy to keep them ordered. But what about flow? So flow happens because of entropy. So things always flow from high pressure to low pressure, from high temperature to low temperature, from high concentration to low concentration, right? So flow always goes from hot to cold. So if I put my ice cream in the oven and I turn the oven on, the ice cream does not get colder, it gets warmer, right? The heat from the oven flows into the ice cream, the cold ice cream, and then it melts the ice cream. So it goes from hot to cold, not the other way around. High concentration to low concentration. If I have a spray bottle and I spray some cologne in the room, so the high concentration of fragrance where I spray it is going to diffuse, it's going to flow outwards, and it goes from high concentration to low concentration. It's going to continue to flow until it's evenly spaced. Question? Oh, so you're talking about blood. If it has too much solute, why does it go in? That's from osmotic pressure. So, but that also, that's the concentration. But then if you look at the concentration, I mean, it's really the water that's flowing, but then if you think of it in terms of concentration, you're going from high concentration cell to when the cell expands, it's going to be low concentration. So it's not proper to think of it that way. But if you thought of concentration flowing, the concentration flowing would be leaving the cell. But I mean, it's the actual flow is water going in the cell. So you can, that's kind of, you can math model things that are improper. So like electricity, we model as the positive charge moving, but the positive charge is it's a negative charge that moves in electricity, but we model it as a positive charge moving. If you have like a hypotonic solution in your blood, you're going to have water flow into the cells. But I said then flow always happens from high concentration to low concentration. You can model the flow as the concentration of your cell is high, but then when it expands goes low. You can model it as the concentration leaving. So, but that's the difference between mathematics and real life. So, what real life mean like actual physical processes. So, thermo fits with math. So, what you would model, what the thermo would model would be the concentration leaving the cell, but it's really water entering the cell. Does that make sense? Yeah. So, okay. Okay. Well, so and other things flowing by pressure. So, water pressure always goes from high pressure to low pressure. Also, gases. So when we have pipelines, gases flow. We always have high pressure at the origin and low pressure at the output. So the gas will flow going towards the lower pressure. And the water too. Also, we have the water up high. So you have the water tanks up high, and when you turn on your faucet by gravity pulling down, or you have a water pump, or the water pump puts pressure on it. So, okay, so let's look at these processes. Which one has a positive delta S? So which one is the entropy increasing? So you go from an ordered state here to a less ordered state here. So this one, part A, entropy is increasing. So here you have a very disordered state to where it all orders itself up into one area. This process, entropy is going to go down. And this one here, if you look at this one, you have disorder here to order here. So actually, entropy here also is going down. So if you can look at these in terms of where it's organizing, and the organization, except for the first one, the organization is going from less organized to more organized. And generally speaking, so entropy is in general going to flow towards more increase. So I keep on using the words in general. Can you break entropy? The answer is yes. Yes, you can. It's just extremely unlikely. So an example I like to talk about is like Skittles. Like if you take a bag of Skittles and you take it out of the bag and you rearrange it by color. So if I put all the red on the bottom of a jar, orange on top of that, yellow, green, purple, so I have like a jar perfectly organized Skittles by color. What's going to happen if I shake the jar? Is it gonna go randomly? The answer is probably yes. Now, is it possible? Can I take a bag of Skittles, pour it into a jar, take the jar, shake it up, and then have everything line up perfectly by color? Is that possible? Yes. Yes, that's possible. Is it likely to happen? No, not likely to happen. How long would I be shaking the jar, until it lines up perfectly? And it'd probably be, I'd imagine it'd be years. I don't know. I don't want to calculate this out, but I'd imagine it'd be a long time. It'd probably be like years or centuries, right? And that's like with 200 Skittles. So what if I have a bigger number? Like 6 times 10 to the 23rd of something. How often is there going to be a significant change in entropy? And the answer is very, very, very infrequently. So it's possible, but it's very unlikely. So that's entropy. So other questions? Okay. Some other terms. System. One of the things with thermodynamics is picking your system, and you pick your system so that the math is the easiest. So, and in future classes, the boundary conditions. And then everything else is the surroundings. In change is always final minus initial. So the change in entropy is always a final entropy minus the initial. And also the entropy of the universe is the system plus the surroundings. So this is how simplistic we are here in chemistry and science. We define our system. So if I call my system this green water bottle, the system is the water bottle. The surroundings are the rest of the cosmos. And so the system plus the surroundings is the entropy change for the universe. So the second law of thermodynamics is that the entropy change for the universe is always greater than or equal to 0. So how can you have no entropy change? If there's no heat transfer. So entropy, one of the definitions of entropy, remember, is Q is heat transfer divided by temperature. If there's no heat transfer, there's no entropy change. So entropy change in the universe. And so also entropy change the surroundings. We'll use this equation soon. The entropy change for the surroundings is the opposite of the enthalpy of the system divided by the temperature. So that's just the heat transfer. At a constant pressure, that's the heat transfer. So, all right, so a couple also things. So for states of matter, solid is the most ordered, has the lowest entropy. Liquid has slightly higher entropy. It's not as ordered. Gases have the highest entropy. And so also moles of gas. So when you have a chemical reaction like this one here, you have 2 moles of gas joining to form 1 mole of gas. The entropy change for the system is negative. So going from 2 moles to 1 mole. So having 2 socks and folding your socks into a dimer sock pair, you went from 2 random particles to 1 random particle. Entropy for that goes down. Entropy goes down by proportional to the number of moles of gas. So calcium carbonate, it's a solid. So limestone, you heat it up, it forms carbon dioxide and lime. So carbon dioxide and calcium oxide. So taking limestone, you heat it up, you form lime, and you form carbon dioxide. This process, you have 2 solids. Well, you have a solid and you're generating a solid and a gas. Since you've generated a gas, your entropy has gone up. So let's do this for a problem. Are we answer any questions? I know I've talked a lot today. So look at this reaction here, combustion of propane. So we have propane plus 5 oxygens forming 3 carbon dioxides and 4 waters. And the enthalpy of the reaction is exothermic negative 2044 kilojoules per mole reaction. So, and calculate the entropy change in the surroundings associated with this reaction at 25 degrees Celsius. So it's going to be delta S of the surroundings is going to be minus delta H system over temperature. It's going to be minus a minus 2044 kilojoules per 298 Kelvin. And maybe I'll go ahead and so 2,044,000 joules divided by 298 Kelvin. And in doing so, you get 608.60 joules per Kelvin, or 6.86 times 10 to the 3 joules per Kelvin. So that's the units on entropy, is energy joules divided by temperature Kelvin, joules per Kelvin. And determine the sign of entropy for the system. Surroundings also, you can see the sign is positive. So the surroundings, entropy is increasing for the surroundings. So determine the sign of entropy for the system. Well, if you look at the system, you have 6 moles of gas. So 1 mole of propane, 5 moles of oxygen, 3 moles of carbon dioxide, 4 moles of water, it goes to 7 moles. So you're going from 6 moles to 7 moles. You are increasing the number of gas particles. Therefore, the delta S for the system is positive. The entropy is going up. So the system is becoming more disordered and the surroundings are becoming more disordered. So what is the entropy change for the universe? So delta S is going to be delta S universe. Delta LS universe is going to be the delta S of the system plus the delta S of the surroundings. So it's a positive number plus a positive number. And when you add 2 positive numbers, you get a positive number. So the entropy change for the universe is positive. Will the reaction be spontaneous? And the answer is yes. The reaction will be spontaneous. And again, though, this doesn't tell you how fast. So this analysis with thermodynamics tells you that this reaction will be spontaneous. It's actually spontaneous at all temperatures, but doesn't tell you how fast. So at above the flash point, so if you have a flame, if I have a flame and I put propane into a flame, it's gonna keep on burning. It'll burn very quickly. What happens if I release a little bit of propane in the room? So, I mean, if I have a gas grill, you know, what happens if I just turn on the gas and let a little bit of propane go into the grill? You know, and I seal the grill up. Is that going to react to the oxygen in the grill? The answer is yes. What happened right away? It'll be really slow. So at this temperature. At a higher temperature, though, oh yeah, it'll happen right away. But that's kinetics. That's not thermo. Thermo can't tell you how fast you get there. It only tells you if it'll happen. And this tells you that this reaction is going to happen at any temperature. So at least any temperature that you have all these as gases. So any questions so far? Well, so recap for this one. What is the entropy change of the surroundings? So we use the change in surroundings is the heater reaction, opposite of the heater reaction divided by the temperature. And we get a positive 6.86 kilojoules per Kelvin. And is the entropy change for the system? We go from 6 moles of gas to 7 moles of gas. We increase the amount of moles of gas. Because of that, the system is increasing its entropy. What is the sign of entropy of the universe? Well, the system is increasing in entropy. The surroundings are increasing with entropy. So positive number plus a positive number is always going to be a positive number. And since the entropy change, the universe is increasing, this process, reaction, whatever, will be spontaneous for any time that it's available. But again, we don't know the rate. Questions of this? Okay, and here is the last part of this. So we have 2 nitrogens plus oxygen in equilibrium with 2 dinitrogen monoxides. So, and the enthalpy change for this reaction is positive 163.2 kilojoules per mole reaction. What is the change in entropy for the surroundings at 25 degrees Celsius. All right, we have 1 minute of class left. This is a pretty easy one, I think, hopefully. It's just, answer is B. So it's just, don't forget to put the kilojoules and the joules. So 1,600,000, I'm sorry, now I have too many. That's right, 163,200 joules divided by 298 kelvins gives you negative 548 joules per Kelvin. So, and it looks like anybody have any questions in the last less than a minute class? Okay, then I will leave it at that.